So we defined electric flux for a very simple case where we had this rectangular surface and a uniform E field. But let's suppose that we have a more complicated surface. And I'll just draw it like this. Again, this is what we call an open surface. And on this open surface, suppose we take a small, on this open surface first, let's draw our electric field, which is non-uniform. And the surface is a curved shape. How can we calculate electric flux through this surface, which was, remember, how much of the electric field is perpendicular to the surface? Well, what we do is we choose a small little patch of the surface. So let's choose a small area patch, and I'm going to call this patch here delta AI is the size of that patch. It's my ith patch. And I have a unit normal, Ni. And suppose on this surface, my electric field is Ei. Then exactly how we consider the small rectangular patch, the flux delta phi is just the electric field dotted into the area element, which is the electric field dotted into the unit normal I times, and let's call that delta A times delta AI to show that it's a small size patch. Can make that look a little bit better. Delta AI. And this represents the electric flux through this small patch. Remember, this is how much of the electric field on the ith patch is normal to the surface. In here, we could call that the angle theta I. Now, if we want to calculate the electric flux through the entire surface, what we would like to do is just add up a bunch of patches. So we divide our surface into n patches, and we define the electric flux on this surface. I'm going to put an index n here. It's the sum, I goes from 1 to n, of the electric flux through, that little n is the unit normal on the ith patch, times delta AI. Now, again, this is a measure of how much of the electric field is perpendicular to each patch times the area of the patch. And I'm just summing up all of these patches. Now, obviously, this sum will depend on how I make this grid of patches, and in fact, the size of n. So what we would like to think of is for each value of n, we get a number. This is a scalar quantity. It's not a vector quantity because we're taking a vector dotted into another vector, which gives us a scalar. And by the way, the units here have the units of the electric field, which remember is newtons per coulomb. So this is what we mean by our units. That's the units of the electric field times meters squared. Now, for each value of n, we have a number. And if we take the limit as n goes to infinity, then what we're getting is really a sequence of numbers. For each value of n, I get a different number. And what I'm looking at is the limit of that sequence of numbers. And that will give us what we define to be the electric flux on this surface. Now, it's very awkward to write down every single time you want to calculate the electric flux this limit of a sum of numbers, and then to analyze that sequence. So mathematicians have a special notation for this. They write this as the integral over the surface of the electric field dot n hat dA. And what they're imagining here is they have an infinitesimal patch which has area dA and NA and an E field A. And so by dropping this index I, they're just imagining an infinitesimal area patch. And this integral is really this summation process. And this mathematical object is called a surface integral. Now, I should say that in principle, surface integrals are difficult to calculate because you need the shape of the surface, and you have to know how the electric field varies over that surface. And in your math courses, you'll learn how to do these types of surface integrals. In physics, we'll try to consider some very special cases in which the type of surface we pick has a known geometry. It could be cylindrical, spherical, and so we know what the area is. And not always, but most of the time, we'll pick an E field that is perpendicular to the surface and constant in magnitude over the whole surface. So evaluating these integrals will be reasonably straightforward. But the important thing is to understand conceptually what we mean by electric flux.